Hello, welcome. This is AQA's A2 Physics. This is Unit 5, June 2014. Okay, so first bit of information we're told is about half-lives. In particular, the half-life of carbon-14, which is 5,740 years. And we're asked to work out the decay constant. Now, there's a quick way of doing this, and the way the equation is built, I will come up with the answer to that in another video. But essentially, we have to use the half-life equation, which is T to the half-life is equal to ln2 over the time decay constant. Okay, and the time period is in years. Okay, not seconds, because obviously, if it was in seconds, it would be hundreds and hundreds of zeros long. Okay, because it's such a big number. So obviously we therefore say the time constant is in years as well. Okay, so if we're given a half-life in years, then the decay constant will also be in per year. Okay, so we know it's 5,740 years. Obviously ln2 is just a number over lambda. Okay, which is decay constant rearranged to get lambda. Okay, in other words, times both sides, divide both sides by 5,740 and times both sides by lambda, sorry, and you should get 1.21 times 10 to the minus 4, okay, in per year. Given the units this time, but just be aware you might have to put them in. Right, okay, so that's 2A part 1. 2A part 2 is saying a piece of wood from an axe handle found at an archaeological site as a 0.375 times as many carbon-14 atoms as an equal mass of living wood. Calculate the age of the axe handle in years. Now the key thing here is we're not given a starting number. Okay, in other words, because obviously the equation we have to use, we know we've just worked out the decay constant of carbon-14, so the decay constant of this is also going to be exactly the same, so you could just copy your answer from your calculator in the previous question. So it's 1.21 times 10 to the minus 4 per year, okay? And we want to work out the age of the axe handle in years, okay? So we want to work out T. How do we do that? Okay, because the only equation linking these two together is either the activity or the number of nucleons. Okay, and what we're told is that obviously they have a starting number of nucleons which is equal to a certain number. Okay, but the number of nucleons in this particular case, atoms even, is 0.375 what it was at the start. So therefore, the n, no subscript, okay, is equal to the starting number times 0.375. Okay, so we can use them as kind of individual figures, so we can cancel off the n naughts. Okay, now the original equation would be n, which is the number of nucleons at the moment, okay, equal to the number of nucleons at the start, or atoms, sorry, equal to time e to the minus lambda t. Okay. Now, obviously, we don't know the true figure of n. Okay, but if we convert them both to n, say a figure of n naughts, in other words, this n, we know that n, the current number of atoms, is equal to the original number times 0.375. Okay, we can simply put our answers both in terms of n naught, so therefore we can cancel out the n naughts and come up with some kind of answer for this. Okay, so is n naught times 0.375 is equal to n is equal to n naught times e to the minus lambda t. We know that lambda is equal to 1.21 times 10 to the minus 4, okay, and that's times t. So therefore it's just a case now of simplifying the answer. Okay, so we can cancel out the n naughts, so we get 0.375 is equal to e to the minus 1.21 times 10 to the minus 4 times t. Okay, ln both sides, so ln of 0.375 is equal to minus 1.21 times 10 to the minus 4 times t, rearrange to get t, so therefore you will get t as 8,106 years. Okay, just need to check something, just be a second. Sorry, I just needed to double check something. Right, okay, so hopefully that was quite simple once you realise what you had to do. I can see that being quite a tricky question because you're thinking, well, I've not got any raw numbers I can put into this, okay? But as I always suggest with any question, what I would always recommend doing is writing down exactly what you've been told, okay? Because if you just look at a paragraph of information, it's hard to pick it out. So as I said, in this question we were told the decay constant, obviously, well, we weren't told it, we worked it out, so as we know, parts questions are going to be related, especially if it's A part 1 and A part 2, okay? We were asked to work out the time, okay, in years, and we were told we didn't know the original number of atoms in this sample, okay, but we know that the remaining number of atoms are 0.375 times what it originally was, okay? So, just from that, okay, if we're not told the original number of new atoms, or we didn't already know that from the previous part in the question, which we didn't, okay, therefore we have to use, they wouldn't have said that if we didn't have to use it, okay, and the only equation in radioactivity that links the number of atoms, the time and the decay constant is this one, okay, so therefore it has to be something to do with this equation, and as I said, we weren't given the raw figures, so therefore we had to adapt it so that it didn't matter. We could go around using the raw, without using raw figures. Okay, so therefore we had to cancel these ends out, but clearly they're not the same. Okay, one's the starting number of nuclei and one's the current. Okay, so therefore we had to convert them into both the current, so we had to convert them into both n, okay, or we had to convert them into both being n0, which was a more sensible idea because we've got a number associated to that. Okay, so therefore we used that and then cancelled down again, and got the time. Okay, so essentially that's the working out for this, and that's how you should think because it is quite a common question. Okay, maybe not to do with the number of atoms, but they might ask the activity rate. Obviously, with the activity rate, you could use a series of different other equations in the actual exam. But as I say, it is imperative that this way of thinking is something that will come to you quite naturally after a few questions. Right, okay, so that's 2A really over and done with. 2B is just kind of more a theory-based part of the question. Okay, so it says for 2B, suggest why the method of carbon dating is likely to be unreliable if a sample is ... So these two parts to 2B, okay, part 1 and 2, are just asking why carbon dating is unreliable in certain situations. Okay, and the first situation, 2B part 1, says if the sample is less than 200 years old. Now for this part of the question, you have to actually think of the graph. Okay, now I said I was going to rub it out. Right, okay, so I don't know if you can quite see this very well, but obviously you can look in your books. It's an exponential decay, okay? So, as you can see, this, if you draw it correctly, this is about 200 years here, okay, here. And in the first 200 years, the gradient is extremely steep. And then beyond this, okay, beyond 200 years, up to a certain point, can't remember exactly what that is, but the gradient is kind of a lot less steep. And this means, if the gradient is a lot less steep, then you can be in a few years and the change of nuclei won't be that different, okay? So you've got basically a more accurate understanding because the gradient's less, so you can more clearly dictate where the number of nuclei changes, okay? But in this initial period, it changes so rapidly, it's hard to measure. It's like if you think of dropping a ball from a height and you just, rather than throwing it down a slope, okay? It's harder to measure the acceleration if you drop it vertically because it's going to be going faster, okay? Whereas if you drop down a slope, obviously you've got friction, so the acceleration is going to be less. But the principle remains the same. So how does this relate to this question? Well, 2B part 1, basically, if it's less than 200 years, there's such a rapid change in the number of nuclei, it's hard to measure out how old it actually is. Okay, so that's 2B part 1. 2B part 2 says, well, if it's more than 6,000 years old, again, we're looking at this graph. Now, as I said, this is the ideal period. But obviously beyond this number, okay, which that's really flattened out, it's kind of the same thing as this almost. That the gradient isn't changing at the right pace, okay? So that the number of nuclei will be so small that we can actually detect the change in years, okay? So you could have that, or you could say the background radiation rate of carbon-14 might actually be greater than the number of carbon-14 atoms being emitted from this sample, okay? So, as I say, you could look online for that, but the mark scheme is fairly quite self-explanatory, okay? Well, thanks for watching. See you in the next question.